but then if the barrier height is not so large, you do have the correction term, right? So you have quantum number +1 plus or minus. So this in effect change your quantum number a little bit, the location of the quantum number a little bit, because it's split it. Furthermore, it's split into two values. It could be a positive slightly above your normal and slightly below your normal. Okay. So what I say here. So this is the main the punchline of what I want to show you is that the first term in star, this is equation star, is like the single square well, right? It's like the single square well. If we take alpha, the barrier height, to infinity, then it converts back. Then this correction term drops out. However, if the barrier height is finite, not infinite, then what happens? What happens is that your quantum number is split into two quantum numbers, right? So the energy, so if the k value is split into two, your energy is also split into two. So for every single square well, if you have double square well, you have two energy very close to each other, nearby to this m value that you got. Okay, so this is a nice result. So you have each energy state is split. And eventually, the energy level in the single square well case is split into E1, E2 in the double square well. And eventually, because this energy level splitting, because you can see, right? So if you go back to this here, so I have one energy level. Because of this barrier height, I have starting to have two energy level for this, right? And for every energy level in the single square well, I will have two in double square well. And this is quite interesting results because almost as if this square well sense the presence of the other square well and starting to respond to this depending on the barrier height. Okay, so this splitting eventually give rise to this band gap if you carry out the math. Okay, so that's the beauty of this quantum mechanics, if you like, that you can show that in a very rather simple, but if you take out the math, the result is rather quite easy to understand. Just the quantum number is modified, the wave into two, into effectively with some correction term, plus or minus, one plus or minus some correction term, depending on this barrier height. Okay. Let me go back. So these are a little bit more math than probably people would like to see, but I think it's useful to even if you may not be able to solve it, you may not have quantum mechanics background to see all this, but you should have a sense of where it's coming from, and I think it's important to show you a little bit of this, the origin of these, where it's coming from. Okay, so we have two square well, and the next step, of course, is to extrapolate to periodic, infinitely long chain, right? So here we have two square well, one next to each other. Now you can have 3, 4, 5, and then infinite number of this thing to create periodic functions. And this periodic potential, of course, stimulate the location of individual atom, and this potential lead to something called a Bloch function, and we'll see. We'll extend. Okay, so here, if we extend the potential to an infinite periodic one-dimensional box, right? So we have two square well now, infinite dimension. We get the so-called Bloch function. So let me just give you a very quick. Again, I don't intend for you to derive this, but I just wanted to give you a background, a feel for this, because I think it's important to have a little bit more meat to see where these things come from. So here we're looking at the electron in a periodic potential, right? And first of all, when we do this, we define a Bloch function. And what is a Bloch function? When we hear people say these in solid-state physics course, a Bloch function is simply a wave function. Has a plane wave, right? Look at that. E to the minus, e to the I, k dot r is the form of a plane wave, right, moving as a plane, hitting this, and then you have this function in front. This u of k of r has the period of the crystal lattice. So this is the periodicity. Control the periodicity of your lattice. Okay, and how do I define periodicity? I can define periodicity by the location of my atom. Okay, so if I have my points, right? This is my location R. Okay, and this is R plus T, a translation vector, right? And this is this point is R plus 2T. Let's say like this, and so forth, right? This is my infinite chain that I got, right? In some direction. I don't care which way. And this, so when we say periodic, what does it mean? It means that this wave function, if I'm here at this point, I would not see any different if I transport myself by the periodicity, by t here, right? So the function that I see here must be the same as the function I see here, or here, or here. Mathematically, what that means is that if u of r, this function depends on r, should be the same as u r plus t. If I move myself by t amount, the two functions should be identical. And if I move myself by 2t down here, the function should be identical. Move myself by 3t should be identical, and so forth, right? So that's how you define periodicity when you sort of move yourself. Mathematically, you define this periodic structure of this function imposed on this. Now, of course, you may say, well, why you do that? Well, because if these are the location of my atom, I would expect that none of these atoms is special, right? So if I can pick any one at random, I should not see any difference. It should not depend on where I am, because I'm in this periodic function. Anywhere I locate myself, it should look the same. If I base myself here, 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 or here, right? So at any of these points. So that's where the periodic function comes in. This gives us the periodicity that we need in a lattice. Okay. So how do you get? So first of all, this is the definition of Bloch function. You have essentially you have a periodic function times a wave function. That's the Bloch function. Okay. And you start off to get to this point. You start off with a periodic potential. Again, as physicists, they like to think of forces, and forces, of course, is connected to the gradient of the force to give you the potential, right? So, so the potential, they like to think of in terms of energy, and potential is energy. So this is how we think in physics terms. So you start off with potential. They always define potential. So this is my potential, and I can define my potential in terms of a periodic function, right? E to the I gx, right? G, as you may recall earlier on, part of the course, G is the reciprocal vectors, right? Reciprocal space vector. X is the real space vector. So this is like going back. That's something that we see before. And okay, and we have U here, right? U is some linear combination, some constant. So we're summing over. You can think of this as a power series expansion. You're expanding this thing in terms of some coefficient, right? Times e to the I g dot x, right? And you can rewrite this, and g here sum over from minus infinity to positive infinity. But you restrict g to just positive number, in order 0 to positive infinity. Then what do you need? In order to get the same series, you have to add e to the minus I g x, right? The negative side, right? Because these two sum are the same, except I write it in a different way. Here I write two series, one from 0 to the negative side, and whereas the other one I write continuously from negative infinity